Did you know there's a scientific law that's over 350 years old, but it explains everything from the fizz in your soda to how you're breathing right now, and even why scuba diving can be so dangerous? It's called Boyle's Law. And today, we're going to dive right in. So let's start with a really high-stakes puzzle. Picture this. You're a scuba diver, deep underwater. The pressure around you is just immense. Now, you shoot up to the surface, maybe 100 feet in just a few seconds, and suddenly, you're in absolute agony. Or even worse, what in the world is happening inside your body? Well, the culprit is something called decompression sickness. You've probably heard it called the bends. See, as you come up to the surface, the pressure around you just plummets. And when that happens, gases that were dissolved in your blood, mostly nitrogen, suddenly come out of solution and form tiny bubbles. The real problem? Those bubbles expand, they can block your blood flow, and that's what causes a world of pain and can even be fatal. Okay, so here's the crazy part. The science that explains this very modern problem, well, it was discovered centuries ago. I'm talking long before anyone had even dreamed of strapping on an air tank and exploring the ocean. So let's hop in a time machine and go all the way back to the 1600s. You've got this guy, Robert Boyle, an Irish scientist, who was a real pioneer of doing actual experiments. Then, a little later, a French physicist named Edmé Mariotte was working on the same thing. And working independently, they both stumbled upon this fundamental invisible rule that governs how all gases behave. And here it is, the big reveal. This is Boyle's Law. It basically says that if you take a certain amount of gas and keep its temperature steady, its pressure and its volume are, well, they're like two ends of a seesaw. When one goes up, the other has to go down. It's that simple. But what does that really mean? You know, in the real world, this idea of an inverse relationship is the key to everything. So let's really break it down. Think of it like this. When you crank up the pressure, you're basically squishing all those tiny gas particles together, forcing them into a much smaller space. The result's a low volume. But if you let up on that pressure, those same particles are free to spread out, take up more room, and boom, you have a high volume. So what's happening on a microscopic level? Imagine you've got a box filled with bouncing balls. If you suddenly make that box smaller, what happens? The balls have less room to travel, so they're going to hit the walls way more often. Each one of those hits is a tiny little push, and all those extra pushes add up to a much higher pressure inside the box. And of course, scientists have a beautifully simple way to write this down. Don't let the math scare you, it's actually super straightforward. P1 times V1 equals P2 times V2. All that means is that the pressure you start with times the volume you start with is always going to equal the pressure you end up with times the volume you end up with. That product, it's a constant. Let's just plug in some simple numbers to see how this works. Say you have 10 liters of gas at 1 atmosphere of pressure. Okay, 1 times 10 is 10. Easy. Now, what if we double the pressure to 2 atmospheres? Well, the law says the volume has to get cut in half, down to 5 liters. And what's 2 times 5? Still 10. It works every time. It's this perfect, predictable balance. And just like that, we're back to our diver. See, deep underwater, that immense pressure keeps nitrogen gas squished into tiny, harmless volumes, dissolved right into their blood. But when they shoot to the surface, that external pressure, our P value, drops like a rock. And what does our formula tell us? If P goes way, way down, V, the volume of that nitrogen, has to go way, way up. It literally expands inside their veins, forming those dangerous, deadly bubbles. Okay, so the diver example is pretty dramatic, I'll admit. But the truth is, Boyle's Law is working all around us, all the time, in some really cool and surprising ways. Let's take a look at where else you can spot it in action. Just take a breath right now. When you do that, your diaphragm expands the volume of your chest. That bigger volume means lower pressure, and air from the outside just gets pulled right in. Or think about a can of soda. It's packed under super high pressure to keep that carbon dioxide dissolved. The second you pop the top, the pressure drops, the gas volume explodes, and you get that satisfying fizz. It's in syringes, spray paint, heck, it's even what keeps astronauts alive in space. A spacesuit is just a personal container designed to provide enough pressure to stop their body fluids from literally boiling in a vacuum. It's everywhere. And you know, the way Boyle figured all this out was just brilliant in its simplicity. He took a glass tube, bent into a J shape, and trapped a little pocket of air in the short end using mercury. Then he just started pouring more mercury into the long end. That increased the pressure on the trapped air, and he could just watch and measure as its volume got smaller and smaller. It was such an elegant experiment, and it's what revealed this perfect mathematical dance between pressure and volume.
Now, like a lot of laws in science, Boyle's law is a fantastic model, but it's not perfect. It works by describing something called an ideal gas. And, as you can probably guess, in the real world, gases aren't always quite so ideal.
So, an ideal gas is basically a theoretical concept. It's a gas where the particles themselves are just massless points that don't take up any space and never interact with each other. But real gases, they're made of actual molecules. They have a real size and they can be a little sticky. And when you push them to the extremes, those little differences start to matter. A lot.
So when does the law start to break down? Well, two main situations. First, at incredibly high pressures. If you squeeze those molecules so close together, eventually you can't ignore the fact that the molecules themselves take up space. And second, at super low temperatures. When you get things really cold, the molecules slow down so much that their natural attraction to each other takes over, and they start to clump together, eventually turning from a gas into a liquid.
But look, even with those extreme exceptions, the core idea that Boyle discovered is just so powerful. And maybe the best way to think about it comes from the man himself.
Here's a really cool piece of history. Boyle never called it Boyle's Law. When he first published his findings, the title he used described the spring of the air. And isn't that just a perfect metaphor? You squeeze air, it pushes back. You compress it, and it wants to expand, just like a spring. It's such a simple, intuitive idea, and it completely changed how we understand the world.
And that really makes you wonder, doesn't it? Boyle found this invisible spring that governs how the air all around us behaves. It leaves you with a final thought. What other invisible springs, what other hidden rules are out there right now, quietly shaping the world we see and touch every single day?